Hello, this is Dongsu from the Applied Superconductivity Lab. Today we'll learn about post-quench analysis. In this lecture, we will cover the post-quench analysis in 3 sections. First, we define the current flow in the composite superconductor using the two-fluid model. Second, we discuss the post-quench analysis in the setting of the two-fluid model and compare it with the stability analysis in the stability chapter. Finally, we conclude this lecture by introducing the following lectures that are aligned with the post-quench analysis by protection method. First, we define the current flow in the composite superconductor, consisting of the superconductor and matrix layers. As the operating current enters the composite superconductor, the current flows through the matrix and superconductor layers, making the addition of superconductor current and matrix current equal to the operating current. Thus, the two-fluid model used in a composite superconductor describes the current behavior flowing through the matrix and superconducting layers. These currents are determined depending on the magnet operation in the stability analysis or the post-quench analysis. In the stability chapter, we have already defined that the whole operating current flows into a superconducting layer in the stability analysis, and this is the moment when the superconductor is operating without problem. If we define the quench event as occurring at t equals 0 time, the composite superconductor is still in the stability analysis, and current flows through both the matrix and superconductor even though the operating current is larger than the critical current. This situation occurs right before the quench event, and we have already discussed it in the previous chapter. However, the post-quench analysis differs from the stability analysis in that the whole current flows through the matrix layer right after the quench event. For this current behavior, we study the stability of the quenched magnets and analyze the protection method for the post-quench analysis. Finally, we introduce the magnet protection methods for the post-quench analysis, which will be covered in the following lectures. First is the Z-function. A physical quantity required for temperature rises from initial to final temperature in the adiabatic heating under constant current. Z-function has an equation, and the critical point is tau Ah, which is the heating duration from initial to final temperature. As the heating duration is more than NZP time and through the enthalpy analysis, if the result from the enthalpy analysis is in the safe range, then the magnet is self-protecting. If the result is risky, the magnet is permanently damaged, which needs more protection. The magnet is also in permanent damage when the heating duration is less than NZP time. The concept of the enthalpy analysis may be briefly introduced in the Z-function lecture. For the magnet needing more protection, the protection circuit consists of passive and active protection. Passive protection consists of self-protection in which shunt resistors or diodes dissipate energy. Active protection has systems such as detect and dump and detect and activate heater, which will be covered in the protection heater lecture. In this lecture, we have seen the current behavior in the composite superconductor using the two-fluid models in which the current flows through the matrix and superconductor. Different from the stability analysis, the post-quench analysis shows that the whole current flows through the matrix layer. Thus, we study the stability of the quenched magnets and analyze the protection methods using a Z-function, protection circuit, and protection heater in the post-quench analysis.